Hi, I am Sanjay Patel. Today we are going to prove one more interesting property of continuous functions. We have proved two properties in our last lecture about continuous functions. Let us prove one more interesting property here. First of all, let me write this as a theorem. This is our third result. And we are going to prove that every continuous function defined on a closed interval always attains its minimum and maximum values. More precisely, if f from closed interval ab to r is continuous on closed interval AB, that means it is continuous everywhere in closed interval AB. Okay, then f attains, or you can say f assumes its maximum value. F assumes or attains its maximum value and minimum value and minimum values in or minimum values on this domain, that is closed interval AB. Means we can find some points in closed interval AB at which f of one point, at some point it is maximum, at some other point it is minimum. Let us write in a different way or an alternative way. We know, we have proved in the last lecture, every continuous function defined in a closed interval is bounded, and every bounded function has its maximum and minimum. The important thing is this maximum minimum is assumed at some point in this closed interval. So let f from closed interval AB to R be a continuous function. And since it is bounded and has its minimum and maximum value, suppose the maximum value is say capital M and the minimum value is small m of this function. So I can write that maximum value, which is also called least upper bound. It has least upper bound and the greatest lower bound, which is obtained for this function. So I can write, suppose capital M is the least upper bound, or you can say supremum of fx, where x belongs to closed interval a comma b. Okay, and small m, that is the minimum value, or you can say greatest lower bound of the function, which is also known as infimum of f of x for x belongs to closed interval AB. So if f is continuous and if capital M is the supremum or LUB and small m is the infimum or GLB, then there exist say some points C, comma D in closed interval AB, in closed interval say A comma B, such that f of C is equal to f of C is equal to capital M. Oops, let me remove this. Okay, f of C is equal to capital M and f of D is equal to small m. So we want to prove this thing actually. So remember, every continuous function defined in a closed interval assumes its minimum and maximum value. To understand this, first of all, let us get an idea from say the diagrammatic representation of this extreme value theorem, which says that if a function is defined in a closed interval AB and it is continuous, its maximum value and minimum value is obtained at some points within that closed interval AB. So this is known as, before we proceed, it is called extreme value theorem. Extreme value theorem. We'll call it EVT in short form, extreme value theorem, because minimum and maximum value are the extreme values. So it is also known as extreme value theorem. So before we begin the proof, let us understand it. Oh, let me draw it again. Yes, this is I'm tracking as y-axis. This I'm taking as x-axis. This is say origin, x-axis and y-axis. And I will consider some continuous function on closed intervals. I will try to draw a continuous function in some closed interval in this picture. So let me take some 2 points, say closed interval a comma b, like this. This is a, this is b, and let me draw now some continuous curve between a and b. Say somewhere something like this. I can draw a continuous function in this region between a and b, closed interval a and b. So something like this. This is my continuous curve, or you can say continuous function between a and b. And you can see here in this graph that this is the minimum value of the function Okay, and this thing here, it is the top, it is the peak, that is the maximum value of the function. So this is continuous curve and it attains its maximum value and minimum value. But what to prove is this is obtained at some points in this domain closed interval AB. So for this minimum value, if you draw perpendicular from this point to this x-axis, this length is small m, and this foot of the perpendicular gives you the point at which the minimum value is obtained. Let us call it d. So this d gives me the value of the function, say f of d, which is same as capital M. This we can also show on the y-axis. This point is small m, or you can say it is f of d. Same way for the maximum value, this is my maximum value. It is some real number, say capital M, and from this point, which is the point for maximum, if I draw perpendicular again on the x-axis, oops, it is not right. Let me do it again. Say from this point of maxima to the x-axis, a perpendicular is drawn, then we get a point, another point, say small c, so that this length gives you the value of capital M, that is f of c. The value of the function at c is same as capital M. So we want to prove this thing mathematically, which is understood from this picture. This is small m, that is capital M, and we can always find some 2 points C and D, for which at one point you will get maximum and another point you will get minimum value of this function. Okay. So remember, we are going to prove this theorem that if f is continuous on closed interval AB to R, and then we want to prove that there is some 2 points C and D at which function has its maximum value, that is capital M, which is the least upper bound or supremum, and f of d is equal to small m, that is greatest upper bound or the infimum, as we have described here. So let us prove this. I will be proving only one result, say for maximum only, and then you can prove similarly that function also obtain its minimum value at some other point. So here f from closed interval AB to R is continuous. This is continuous function that is given in the hypothesis. Okay, and we know that every continuous function is always bounded. So this f is also bounded. F is bounded on its domain, which is closed interval a comma b. F is bounded on closed interval a comma b. If f is bounded on closed interval ab, it means the range of f which is nothing but the image set of closed interval AB under F, which is denoted by this symbol, and this is actually is given by set of all f of x, such that x belongs to closed interval a comma b. So Rf, that is range of f, is actually this set, and it must be a bounded set. This is a bounded set. If f is bounded function, then its range set is a bounded set. Okay. Since it is bounded subset of R and R is complete, so its least upper bound and the greatest lower bound of this set exist, or you can say supremum and infimum of this set exist. So we can assume, say, the maximum value or the supremum value of this set is capital M. Say suppose M is equal to which is the least upper bound or the supremum of the set f of x, such that x belongs to closed interval a comma b, which is equal to, we can write in the, say, compact form as supremum of fx over x belongs to closed interval a comma b. And also we have minimum value, or you can say the greatest lower bound or infimum of the range, that is set of all fx, such that x belongs to closed interval AB, which is equal to infimum of fx, where x belongs to closed interval a comma b. So these two numbers, LUB and GLB, of the range set of this function exist. We want to prove that for some point this capital M is obtained, and for some another point in the domain the value small m is obtained. I will be proving the result only for, say, maximum, and same way you can prove it for minimum. So M, remember that capital M is the least upper bound of set of values of the function f of x, and small m is the greatest lower bound, GLB, of the function. So let me write. This implies, first of all, one note: since small m and capital M are the minimum and maximum value respectively, all values of the function lies between small m and capital M. So I can write this thing: small m less than or equal to fx less than or equal to capital M for every x belongs to closed interval AB. Yes. And we'll prove the result only for, say, maximum value. That is, there is some point C in the domain that is closed interval AB such that f of c is equal to capital M. So what is our aim is this small m less than or equal to fx less than or equal to capital M. Small m is the minimum, capital M is maximum. So we shall prove that there exists some point C in closed interval a comma b such that f of c is equal to capital M, that is maximum value, or you can say least upper bound of the function fx. This will be proving by contradiction. So suppose, let me write this. First of all, f of c is equal to capital M. We want to prove that there is some c such that f of c is equal to capital M. At least one c exists. And suppose this is not true. Suppose it possible this is not true. So let me write in short, suppose not. Means this statement is not true which we want to prove. So that is there does not exist some point in closed interval AB such that f of c is equal to M. So I can say there does not exist x in closed interval a comma b such that f of x is equal to capital M. So we are assuming that this is not true. So we'll get this thing. There exists some x, there does not exist any x such that fx is equal to M. Fx is equal to M means fx is say not equal to M for whatever x you choose in closed interval AB. There is no c, there exists some c belongs to closed interval AB such that f of c is equal to M is not true means this thing, there is no x in closed interval such that fx is equal to M, means fx is not equal to M for any x. So any x, let me don't write here, let me write this as fx is equal to M, because I have written that does not exist any x in closed interval AB for which fx is equal to M. And let me write the meaning of this in a new line. That is, I can say this implies fx cannot be equal to M for any x, means whatever x you choose for all x, fx is not going to be exactly equal to capital M. So for every x belongs to closed interval AB, fx is not going to be equal to M. In other words, we can say that this implies fx minus M is not equal to 0 for every x belongs to closed interval a comma b. So using this condition, I will be getting some contradiction. So what I want to do is I will define a new function using this last step, that is last condition, fx minus m is not equal to 0. Remember that our aim is to prove that there is some c belongs to closed interval AB such that f of c is equal to m, and we are assuming that it is not true. So we are getting all these consequences, that is fx minus m is not equal to 0 for every x in closed interval AB. Okay, let me call this as star. Fx minus m is not equal to 0 for every x belongs to closed interval AB. And let us define a new function with the help of this star as follows. So define capital F from closed interval a comma b to R. Let me remove this. F from closed interval a comma b to R as capital F of x is equal to m capital 1 upon m minus capital M minus f of x for every x in closed interval a comma b. Okay, and this is a well-defined function because of this star, because fx minus m is not 0, so m minus fx is not 0, so we can define 1 upon m minus fx. So it will not create any problem. So we have taken this new function capital F, and it is defined for every x belongs to closed interval AB from the condition star. Okay. Now this m is a constant. This function small fx is given as continuous function in our hypothesis. It is continuous on closed interval AB, and capital M being a constant function is also continuous. So m minus fx is continuous. So it's a reciprocal, that is 1 upon m minus fx is also continuous, and hence I can say or conclude the function capital Fx is also continuous. So let me write in detail that small fx is continuous on closed interval a comma b, which implies the function capital Fx, which is defined as 1 upon capital M minus small fx, being a reciprocal of a non-zero continuous function, capital Fx is also, capital F of x is also continuous, on closed interval a comma b. So we have defined a new function capital F here and shown that it is continuous on closed interval AB. Okay, remember it is well defined because m minus fx is not 0. And we know that a function, if it is continuous on a closed interval AB, it is always bounded, which we have proved in our earlier result. So the function capital F of x is bounded on closed interval AB. So let me write, therefore, the function capital Fx is bounded on closed interval AB. Is bounded on closed interval AB. So its supremum and infimum both exist. That is, LUB and GLB exist. Or I can say there exists some k. I can also write this way. There exists some constant that by definition of bounded function, there exists some constant k greater than 0 such that mod of capital F of x is less than or equal to k for every x belongs to closed interval AB. You know that mod of x is less than or equal to k for every x belongs to closed interval AB. We can also write in the equivalent form as minus k less than or equal to fx less than or equal to plus k. So I can write this. I can write this as replacing minus k less than or equal to capital Fx less than or equal to plus k and putting the value of capital Fx, we can write it as, because mod of Fx is less than or equal to k, we can simply write Fx is less than or equal to k, because this means Fx lies between minus k and plus k. So m minus small fx, because capital Fx is 1 upon m minus fx. This is less than or equal to k for every x belongs to closed interval a comma b. So we obtain this thing, and this implies if I take the reciprocal here in this inequality, I can write it as m minus small f of x is greater than or equal to 1 upon k. Note that k is positive, so there is no problem in taking the reciprocal here. So this is true for every x belongs to closed interval AB. Now just rearranging these terms in this inequality, we can rewrite it as this 1 upon k I am taking on this side. So m minus 1 upon k is greater than or equal to small f of x. This is true for every x belongs to closed interval AB as it is. So this gives us, we can write in a different form, that is f of x is less than or equal to m minus 1 upon k for every x belongs to closed interval a comma b. Okay, every x belongs to closed interval a comma b. So this says that the number constant m minus 1 upon k, this number is an upper bound is an, let me write the full form, is an, this m minus 1 upon k is an upper bound of the function f of x. Function f of x. But we know that the number capital M is the least upper bound of the function small fx. So let me write that, mention that, but capital M is the LUB of fx over x belongs to closed interval a comma b. That means m is the least upper bound of the function fx. And here we are proving that m minus 1 upon k is an upper bound of fx. That is, since m is least upper bound, the number less than capital M cannot be an upper bound. And here we are proving that m minus 1 upon k is an upper bound of fx. So this is a contradiction. This is a contradiction to the fact that m is the LUB of fx. So I can say that therefore it's a contradiction. This is a contradiction. Okay. And it is a contradiction to the fact that m is the LUB. M is the LUB of fx. Okay. M is the LUB of fx. So m minus 1 upon k is the upper bound of fx, gives us the contradiction. So our supposition must be wrong. Our supposition must be wrong. What was our supposition? If you remember, we have assumed in the beginning that there is no x in closed interval AB such that fx is equal to m. So this thing is wrong. So this thing is wrong means there is at least one element, some element in the closed interval AB such that the value of the function at that point is capital M. So this is wrong. This our supposition is wrong. So we can find some point here. That point I would like to call as some number, say small c. So there is some number c belongs to closed interval AB such that f of c is equal to capital M. So therefore we can write, therefore there exists some small c belongs to the domain that is closed interval a comma b such that f of c is equal to capital M. F of c is equal to capital M. And the same way we can prove, similarly we can prove that there exists some point D belongs to closed interval AB, closed interval a comma b, such that f of D is equal to small m. F of d is equal to small m. So the result is proved, and this is known as extreme value theorem, EVT. Let me write d properly here. So there exists some d belongs to closed interval AB such that f of d is equal to small m. Okay. So thank you.